Well, hello and welcome to the 15th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. Let me remind you what we were doing so far. We were looking at this very important result that we called the fundamental principle, right? Let me write that down. Fundamental principle of algebraic analysis. All right. What was that fundamental principle? So we were trying to solve equations like this, right? Ax equal to b. Yeah, but here remember what we have is this A matrix is now a polynomial matrix of size, let's say G cross Q. Yeah, a polynomial matrix. B is a C infinity function of size G, and X also is required to be a C infinity function, but X is not known, right? And we are asking when is this equation, when is this differential equation solvable? Yeah, the quick answer to this of course is that it is solvable if and only if B, the trajectory, belongs to the image of this operator A. Let me write A as I as well, so that we know even by just looking at it that this is a differential equation. Yeah, but how do you check whether something is in the image? Yeah, how do you characterize the image? It may not be easy, right? For systems of linear equations, there are ways of doing this. As you know, you can find out the basis for this for this image, yeah, and then you can do this checks and so on. But here it turns out that an indirect method, an indirect check for this is more helpful. What is that indirect check? Well, the indirect check has something to do with the linear algebraic idea that if you take a subspace, yeah, and look at its orthogonal complement and then look at its orthogonal complement, it should be equal to the space itself, right? But we should not go by this analogy too much. Let us try and see this directly. So the fundamental principle says something like this. So the fundamental principle says that, okay, let me rewrite the equation. A is I acting on unknown x is equal to b. It is solvable for x, solvable for x in C infinity if and only if. Now see, for all polynomial vector of size 1 cross G, you see it is a row vector. For all R xi satisfying R xi A xi is equal to 0, we must have R xi acting on B equal to 0. Okay. So, for all such row vectors which algebraically satisfies this equation, must also, when acts upon the trajectory B as a differential operator, must produce 0. Then and only then can we say that this x can be found. Yeah. Why did I say orthogonal complement of orthogonal complement? Why is it related like that? Well, you see, when I am doing algebraically, when I am saying that R xi is a row vector which is such that R times A is equal to 0, what does that mean? That means, roughly speaking, that this row vector R is orthogonal to all the columns of the polynomial matrix A xi, the standard meaning of orthogonality. Let us not, please do not go by these terms very too seriously, because I am just saying loosely. Yeah, I have not defined what is orthogonality for polynomial matrices and polynomial vectors, These ideas are not so simple. Yeah, I am just saying that this is a row vector which when taken this dot product, the standard dot product with the columns produces 0, yeah, polynomially. Okay. Now, yeah, then I am saying that whenever R psi is orthogonal to the columns of A, that means it is orthogonal to the column span of A. R psi acting upon B must also produce 0, which means now functionally this operator is orthogonal to B. What that means essentially is that R psi annihilates this trajectory B. So, everything that is orthogonal to this guy is also orthogonal to B, right. So, that means B must belong, roughly speaking, B must belong to, so B must be orthogonal to the orthogonal complement of, so B as a trajectory is orthogonal to things that are orthogonal to image of A, which means B must belong to image of A orthogonal complement, which means this is equal to image of A. That was the idea, I mean that was the analogy, but please do not go by this analogy very seriously, because this is not a proof certainly. Yeah, how did we prove this? If you remember, look at the other lecture, look at the previous lecture. We proved this through what is known as a Smith canonical form. What we needed for this was actually not the full Smith canonical form, but a quasi Smith canonical form, where we said that given any matrix A psi of size G cross Q, it is always possible to find orthogonal, not orthogonal, sorry, my bad. Here we do not talk about orthogonal matrices, we talk about unimodular matrices. Sorry, I need to fix the sizes as well. Right. Yeah. U psi is a G cross G unimodular matrix. Yeah, and V psi is a Q cross Q unimodular matrix. So that A psi can be written as U psi D psi V psi, where D of course is a matrix of the same size as A, but it has a very special structure. How does it look like? D psi looks like this. D psi is so this is a diagonal block, diagonal matrix with R polynomial entries, and remaining are filled with zeros, right. And these polynomials are special because they have the property that each polynomial divides its successive polynomials. That is this full Smith form, but for our purposes it is enough to have Smith form. It is enough that we do not, I mean we need not insist on this special property. As long as it is a diagonal matrix, it is fine for us. Yeah. So, please go back and check the proof that we did of this of fundamental principle using Smith canonical form. I will just go through a very brief sketch. I will just rush through the proof using Smith canonical form of the fundamental principle, right. So that it helps you to understand it better when you go back to the previous lecture and see the full proof. Okay. So, what was the proof? Well, the one direction is easy, you know, A psi x is equal to B. Suppose it is solvable. Suppose there exists an x in C infinity such that A psi x is equal to B. I mean a solution exists, then if you just take any r xi such that r xi a xi is equal to 0, then that obviously means r xi a xi x is equal to r xi b. But this part is 0, so it is the 0 operator acting on a trajectory. Of course, it should produce 0, which then says that r xi acting on the trajectory b must also be 0. Right? What did we do? We just say that okay, we needed to show r xi b is equal to 0, right? That is what we need to show, but we realize that r xi b is nothing but r xi a xi x, because a solution exists, and r xi a xi is assumed to be 0, so this is equal to 0, right? That's simple. So that's one direction. That means let me go back to my my description of fundamental principle. Yeah. So fundamental principle says that whenever whenever r xi is orthogonal to a xi, r xi b must be equal to 0. So what we have proven is this direction, that if solvable, then the assertion is true. So this direction is easy. What about the other direction? The other direction needs us to show that, so we assume that for all r xi of size 1 cross g satisfying r xi a xi equal to 0 algebraically, we must have r xi b is equal to 0. So we have this property satisfied. We want to show that there exists a solution x. How do we show this? We construct a solution. We show that we can get the solution like this. X belongs to C infinity such that it is a solution, that is a xi x is equal to b. So this condition is given, that this condition is satisfied. We need to construct a solution x. That is the proof of the other direction. So for that, what we do is we just look at this guy. We have so we have a xi x is equal to b. We just immediately we want a solution for this, right? This solution it is equivalent to solve this. We obtain the Smith canonical form, right? That is just equivalent to prove that is just equivalent to solving d xi v xi x is equal to u inverse xi b. Now remember, because u is unimodular, u inverse xi is also a polynomial matrix, so it makes sense. So this is what we need to solve, right? We give some new names. We call this guy, we define this guy as b tilde. Yeah, b tilde now is a C infinity trajectory of the same size, right? And then we also define v xi x, the unknown now is defined as an unknown y, which also must be a C infinity function of size, right? And it is now equivalent to solve for this equation d xi y is equal to b tilde. If we can solve for this, we can solve for x easily, because you see how have we defined y? v xi acting on x is defined as y. So obviously now if we know y, we can find out x by doing a v inverse xi acting on y. Okay, so that is why it is enough to solve for y. Now look at the equation for y. How does the equation for y look like? How does d look like? D looks like d1 xi, d2 xi dot up to dr I should use a different letter. What should I use? Rho. D rho psi. These are all zeros, by the way. Yeah, this is the block which is diagonal, and then the remaining blocks are all zeros. Okay. That acting on y1 dot 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 up to y rho, y1, y2, okay, and y rho plus 1 dot 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 up to y q. Okay. This is my y, and that should be equal to b tilde. I am solving for this, but now just look at this form. Yeah, look at this form. When you do this matrix vector multiplication, you can just realize that the equations are nothing but d1 xi acting on y1 is equal to b1 tilde. In fact, I can just replace these by i's, and where I goes from 1 to rho, and the remaining ones are as follows. Remaining ones are, I mean, beyond rho plus 1, beyond rho, starting from rho plus 1 till q, you see it is 0 times yi is equal to bi tilde, isn't it? Just look at it carefully. Okay, right? Yeah, but then such solutions will exist only when, so these are equations like 0 is equal to something. So 0 equal to something will have a solution only when this right hand sides are also assumed to be 0. So just look at this equation and convince yourselves that a solution to this exists if and only if b rho plus 1 tilde up to b g tilde, all of them must be equal to 0. Yeah, then and only then such a solution exists. But what the condition that we have, does that imply that this is true? Right. On the other hand, let me just rephrase. So what I said is that such a solution exists if and only if the right hand side is equal to 0 for all these equations starting from rho plus 1 onwards, right. Yeah, that also it also is important for us to figure out that the other equations are solvable, and they are solvable. We have seen in the last few lectures that when you have scalar equations like this, let me rewrite the equation. Scalar equations like d1 xi y1 equal to b1 tilde, such an equation, such a scalar equation is solvable for all b1 tilde. For all c infinity functions b1 tilde, you can actually solve for it and get a y1 which is c infinity, no matter what this operator is, as long as it is non-zero. Yeah. How do you solve for this? Well, of course, you just have to do this convolution integral and find out homogeneous solutions, and you get a whole set of solutions for such things. We have done this before, and I will give you such problems, such actual equations to solve in the exercises as well. That will give you give you clearer ideas as to how solve such differential equations, such ordinary differential equations. But rest assured that such a solution exists the moment you have a non-zero operator here, and this guy is any c infinity function. So they are solvable. So the first row equations are solvable no matter what, as long as these guys are non-zero, d1 up to d rho are non-zero. But the remaining equations are solvable only when b is 0. So that means this condition must be satisfied. But this was not given to us. What was given to us was that whenever r xi a xi is equal to 0, that implies r xi acting on b is equal to 0. Does this condition, so the point on which this whole proof hinges is whether this condition guarantees that b rho plus 1 tilde, I mean b tilde rho plus 1 up to b tilde g is equal to 0. Does this condition imply this? That is the question. Does it? Well, let us see. Now what do we have? We take an r xi and A xi is equal to 0, right. What does that mean? This means R xi, U xi, D xi, V xi is equal to 0. What does this mean? Now, look at this. This guy being 0, so now let us define this guy as R tilde xi, right. So, this implies R tilde xi multiplying D xi, V xi is equal to 0. Now, because V xi, this is a unimodular matrix, so it has an inverse. So, this product is 0 only if this guy is a 0 vector. You see, remember for matrices as well, for matrices with constant entries as well, when you have a matrix, vector multiplication goes to 0 and the matrix is an invertible matrix. Yeah, such a product is 0 only if the vector is 0, isn't it? Ax is equal to 0 where A is a non-singular matrix, if and only if x is the 0 vector. So, likewise, because B is a unimodular matrix, it is invertible. So, such a product is equal to 0 if and only if this product is equal to 0. But now, look at this R tilde xi, D xi equal to 0, right. R tilde entry wise, let me write R tilde 1 xi, R tilde 2 xi, dot 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 up to R tilde rho xi, dot 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 up to R G tilde xi, yeah, because there are G rows. This multiplies D1 xi dot 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 up to D rho xi, yeah, and the remainings are filled with zeros, and this product is equal to 0. Okay. If this product is equal to 0, what does that mean? What does that mean? This means R1 tilde xi D1 xi must be equal to 0, R2 tilde xi D2 xi, this product must be equal to 0, up to R rho tilde xi D rho xi, this must be equal to 0, yeah, and the remaining ones we just there is no restriction, these guys can be anything. But see, these are polynomial equations, this is a polynomial, 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 and polynomial ring R xi is an integral domain. That's a fancy name for saying that on this, in this ring, if you take two non-zero polynomials and multiply them, you can never get 0. For a product to be 0, at least one of them has to be 0, but we already know that this D1, D2 up to D rho are non-zeros. So, that means all these conditions actually imply that R1 tilde xi must be 0, R2 tilde xi must be 0, and so on up to R rho tilde xi must be equal to 0. So, this means this condition, you see, this condition necessitates that R tilde xi, which is by definition U xi, which is by definition R xi multiplying U xi, this must have the form that it is 0 0 0 row number of such zeros and then non-zero, possibly non-zero guys here, yeah. This is the structure, and because it is necessary for R to be like this, that R tilde has this form, yeah, this means that these guys must be necessarily 0 and these can be anything. So, in fact, you can get the whole set of R xis which satisfy this property, the whole set of R xi. So, this in fact characterizes R xi. So, the set of all R xi such that R xi A xi is equal to 0, that set is equivalent to the set of all R xi such that the corresponding R tilde xi has the structure, first row entries are 0 and the remaining are anything. So, these stars can be filled up as they are to get all possible R xis which satisfies this condition. Now, with that, what now we have R, okay, what have we assumed? We have assumed that R xi A xi equal to 0 implies R xi B is equal to 0. But what is R xi B? R xi B is the same as R xi U xi U inverse xi B, right, which is the same as R tilde xi B tilde, right. Remember how we had defined B tilde? B tilde was defined as U inverse xi B, right, and how was R tilde defined? R tilde was defined as R xi U xi. So, using these two definitions, I realize that R xi acting on B is the same as R tilde acting on B tilde, correct. Now, what is the form, general form of R tilde? General form of R tilde is 0, row such zeros, and then arbitrary entries, arbitrary polynomials, and B tilde is B tilde 1, B tilde 2 dot 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 up to B tilde row, and then B tilde row plus 1 up to B tilde G, right. So, G entries here. So, this is how many entries? G minus row entries. Here also we have starting from this onwards, we have G minus row entries, yeah, and this is equal to 0 for all such situations. So, this I can choose these stars arbitrarily, still I know that the right hand side will be 0. When is that possible? So, choose 1 here and everything 0 here, that will give B row plus 1 is equal to 0. Likewise, choose 0 here and 1 here and 0 everywhere else, that will give us B row plus 2 tilde is equal to 0, and likewise you can show that all of these guys is 0. So, the moment we assume R xi A xi equal to 0 implies R xi B equal to 0, it says that B tilde has the desired form, B tilde satisfies this condition. So, that means we have proven this guy, that this condition implies this, which means we have solvability, right. So, I wanted to give a sketch, but practically I have given you another run through the same proof, but it is okay because it is a very important result, and it is all right to have a multiple look at this fantastic result. But let me remind you what this result was. So, in a way what we have done is that we have given you a check, so to speak, to figure out when such an equation is solvable, right. Now, what we will see in the next lecture is that, and it will sort of keep helping us again and again throughout this course, that if we have, say, a latent variable representation, we have a system of equations where we have manifest variables as well as the latent variables, which were there for modeling purposes. Yeah, remember those Wheatstone bridge circuits we were looking at, and there we were assigning this current, this voltage, each branch voltage currents we were using to write down the equations for the whole system. But ultimately we were interested only in the port variables, port voltage and current. So, how do we get an equation involving only the port voltage and current, where we have equations involving these internal variables as well? The idea is to eliminate those equations, eliminate those variables. Now, elimination of variables is a very standard thing, as we have already discussed before, when we have constant equations, when we have just linear equations. But if we have differential equations and your variables are no longer just numbers, but they are trajectories, in that situation how is it possible to eliminate those variables and still have equations involving only the manifest variables which describe the system fully? It turns out that fundamental principle gives you a fantastic and simple algebraic way of doing this elimination. Yeah, That is what we will see in detail in the next lecture. Till then, take care. Bye.